So problem 3 on our first hour exam gives you this picture. A incline that makes an angle theta with respect to horizontal. There's a block of mass m on the incline, and you're pushing on it with a horizontal force F in the direction up the incline. Now, the first step is to draw a free body diagram, the first requirement, or a force diagram. And so let's do that. Here's an incline. Here's a block of mass m, although you could draw a point particle if you want. The forces acting on it are the weight or the force of gravity pointing down. There's our horizontal force F. And because the mass is in contact with the incline, there's a contact force we'll call the normal force pointing perpendicular to the incline. And then I have to choose the coordinate system for this. Okay, and the best choice will be a coordinate system where one axis, the x-axis in this case, aligns with the incline, and my y-axis is perpendicular to the incline. So that's my free body diagram. Okay, part B says, what are the magnitude and direction of any contact forces? Well, before I start on that, I realize I'm going to need to write out the forces in terms of components along my x and y direction. Well, the normal force is a pure y force, so that's not a problem. But I'm going to need gravity and my pushing force in terms of my x and y directions. So let me make another little drawing to show you how I'm going to do that. So this is again a triangle, like the incline of angle theta, but gravity points straight down, mg. To resolve that into components, parallel to the incline and perpendicular, where that's a right angle, if this angle is theta, then this angle is 90 minus theta over here, and this angle is theta. So that tells me that this component is mg sine theta. I can write that here, mg sub x is equal to mg sine theta. And my y component of the weight of gravity or force of gravity will be mg cosine theta. But that will have a minus sign because it's pointing down in my negative y direction. Okay. How about my normal force? Okay, or not my normal force, but my pushing force. Well, here I'll draw another right triangle. But my pushing force is horizontal. That's F. And I need to break down its components into components along my x-axis, which is this, and perpendicular, so that this is a right triangle. This one's a little bit easier because I already know the angle theta. So the pushing force has an x component, negative F cosine theta, because it's pointing in the negative x direction, and its magnitude is the adjacent to that theta, and has a y component, which is also negative Fy sine theta. So now I'm ready to proceed with part B. And it asks for the contact force, which is in the y direction. So let's write down the sums of the forces in the y direction. Okay, well, I've got my component of the pushing force minus F sub y, or just F, sorry, no sub y there, just F sine theta. And I've got a component of gravity in my y direction, minus mg cosine theta. Okay, and I've got my normal force. So I've got three forces that have components in the y direction, but those have to sum to zero because there's no acceleration in the y direction. So I can solve this for the normal force. It's just F sine theta plus mg cosine theta in my y hat direction. It does ask you for the magnitude and direction with my coordinate system, so I want to put in that y hat. So that's the answer to part B. C asks you to find the acceleration of the block along the incline. Well, I also have my sums of the forces in the x direction equation. That'll give me the mass times the acceleration in the x direction. So I look at my components of the various vectors and I see, well, gravity gives me a component in the x direction of mg sine theta. Normal force has no component in the x direction, but my pushing force does. So my pushing force has a component in the x direction of minus f cosine theta. And I can solve this for the acceleration. The m's like this. So the acceleration in the x direction is equal to g sine theta minus f over m cosine theta in my x-hat direction. Okay. Part D says, well, let's do a common sense check. What happens if theta equals 0 and theta equals 90 degrees? If theta equals 0 degrees, then my expression for the acceleration just reduces to negative f over m, because sine of theta becomes 0, cosine theta becomes 1. So it's just like you're pushing a mass along a horizontal surface with the force F equals ma. Gravity does not matter at all, as expected, so that's good news. At theta equals 90 degrees, my expression for the acceleration gives me, what, at 90 degrees, sine theta is 1, so I have g, cosine theta is 0, so there's no f over m term. So, and the force I'm pushing with against the frictionless surface has no effect on the motion of the mass in the y direction. It just falls with the acceleration of gravity, which also makes sense. Okay, so done with this problem.